Hi everybody, this is the lecture on section 3.1, curves in 2D, parametric curves in 2D and 3D. Given a parameter t, a vector function is r of t equal to x t y t in 2D, or in 3D, x t y t z t in 3D. So often we think of t being represented or representing time, and therefore r of t is the position vector of a point at time t. Okay, graphing the coordinates of r of t for all t in its domain produces a curve in 2D or 3D space. So, for example, let's do one that you've seen several times before, but we'll take a look at it in this context. Let me give you a more general picture also. Just in general, it looks like this, what we're talking about here. You have your x, y, and z axes for three-dimensional space. And then r of t is describing the position of some particle as it travels through space, right? So we'll say a is less than or equal to t less than or equal to b. This would be r of a right here. This vector here would be r of a. This would just be some r of t where t is somewhere in between. And then r of b would be over here, this last one. And if you just keep drawing that particle over time, that point over time, or particle, we often think of it, it just gives you this curve, and you're essentially following some path along this curve. So t exists on a number line, t equal to a, t equal to b, right, on some t-axis. So it takes this line segment on the t-axis and then puts it into 2D or 3D space. So a one-dimensional domain gives you a one-dimensional range. Okay, so let's take some examples of that. If we say x is equal to 3 cosine t, y is equal to 2 sine t, right? Well, what does this represent? Notice that x squared over 9 is equal to cosine squared t, right? And then if I add to it y squared over 4, you get sine squared t. Right, so x squared over 9 plus y squared over 4 is cosine squared plus sine squared, which is just 1. Right, so what we did here is what we eliminated the parameter t. So this is a Cartesian equation for x and y after eliminating the parameter t. And this is the ellipse whose radius along the x-axis is 3 and along the y-axis is 2. So the ellipse, let's see, is this here. Now, how is the motion along this ellipse? How are we going to describe that? Well, check out some different values for t. At t equal to 0, we're at 3, 2. So this is t equal to 0 right here. At t equal to pi over 2, x is 0 and y is 2. X is 0 and y is 2, so we're up here. So as t is increasing, we're moving along the ellipse in this direction. Right, and then at t equal to 3 pi over 2, we're right here. And at t equal to 2 pi, we'd be right there. Now, one could, say, restrict the domain to be, say, from 0 to pi, in which case it would just be this top half of the ellipse. You know, different restrictions you could make. Or say 0 is less than or equal to t less than or equal to 4 pi would be 2 trips around the ellipse. So let's say that 0 less than or equal to t less than or equal to 2 pi. So the motion is twice around the ellipse in the counterclockwise direction. Okay, about something else. So let's say r of t is equal to, so similar to that one we just did, 3 cosine t 2 sine t, and then t. And just say t is bigger than or equal to 0. Well, the x and y coordinates, okay, are again describing in the two-dimensional sense, right, this traversal around the ellipse. And we're just going around and around and around because we're just saying t is bigger than or equal to 0. But then what's going on with the z-coordinate? Well, the z-coordinate is just increasing in a linear fashion. So if we were to draw this ellipse, right, which is the ellipse x squared over 9 plus y squared over 4 equals 1. So that's the surface of that elliptical cylinder, in XYZ space, where this is the x coordinate, this is the x-axis, y-axis, and z-axis. what's being described for r of t is that we start here with z equal to 0, t equal to 0, with x equal to 3, y equals 2, t equal to 0, and then we're traveling in the counterclockwise direction, and the z-coordinate is just making us go up the ellipse in a linear fashion, well, with linear increase. And it's just sort of turning around the cylinder like this. So this is r of t, right? And that shape is called a helix, right? Notice that the surface, it allows us to see the curve better, okay? So the x, y, and z in this function r of t, this vector function r of t, x, y, and z satisfies x squared over 9 plus y squared over 4 equal to 1. So every x, y, and z that r of t describes lives on the surface that is this elliptical cylinder. So then when we draw it on the cylinder, you kind of see it better, right? The cylinder is a surface that is a two-dimensional surface. And then r of t is a one-dimensional curve. So you sort of see the one-dimensional curve living on a two-dimensional surface better than you would see a one-dimensional curve living in a three-dimensional space on its own. I mean, if I drew a helix like this, you could say, yeah, you know, I kind of see what's going on, but I think in our mind's eye, we're kind of seeing that cylinder anyway. But in the absence of a surface along which the curve is drawn, it does become a little bit harder to see the curve. And let me give you an example of that. R of t equal to, say, t squared. Okay, here, x squared plus y, let me put 2t squared. So here, right, the points described by r of t all satisfy x squared plus y squared, well, z equal to x squared plus y squared. So r of t, the curve for r of t, lives on the paraboloid z equal to x squared plus y squared, and that looks like this. So we've got this parabola, and the cross sections for fixed values of z are circles. So we've seen that surface before when we talked about quadric surfaces. So this is z equals x squared plus y squared. So now r of t describes the points, let's do that one in red, describes which points that live on this, t, or 2t squared. Well, the points that satisfy x equal to t, y equal to t, that's just along the line x equal to y. X equals y equals t. That's these points here. So then if we add in the z-coordinate, it just lifts this guy up to the paraboloid, and then that's what we get. For increasing values of t, we're going up the paraboloid like this. Right? So now, I mean, we have a much sort of nicer feel for what that curve looks like because we're seeing it on the surface of that paraboloid. If I was just kind of, to draw it like this, well, it doesn't quite look as satisfying, does it? Right? Because it's in three-dimensional space. It's a curve that's one-dimensional in three-dimensional space, and we kind of have a hard time perceiving a drop in dimension. Two steps a drop in dimension. Sort of a practical example of this would be the following. It's like if you've ever played baseball or softball and you've ever been out in center field. When somebody hits the ball towards you in center field, I mean, if you're not really used to it, it's kind of hard to judge the path of that ball as it's coming towards you. It's harder to perceive it, and that's because the path that the ball is following is a one-dimensional thing, and you're moving around in a three-dimensional space, so it's a little bit hard to judge until you really have a lot of experience, and then then you get a better idea of how to judge that fly ball. All right, there's a couple examples. How about something like this? So consider the cylinder x squared plus y squared equal to 4, and its intersection with the plane 3x plus 2y plus z equal to 1. Okay, 3x plus 2y plus z equals 1. So now I'm not going to draw them on an xyz coordinate system. I'm just going to draw that cylinder. So here's the cylinder, and here's the plane. Just any old plane. We're just going to draw it. And how does that plane intersect the cylinder? Well, it intersects in some kind of oval shape. It's not really an ellipse. It's just, some kind of oval, roundish shape. All right, so that's the intersection of these two surfaces. Give me a vector function, r of t, that describes this curve of intersection of the two surfaces. So what would be a function r of t whose curve is this intersection? Okay, well, r of t equal to x of t, y of t, z of t must satisfy both equations. X squared plus y squared equals 4, and 3x plus 2y plus z equals 1. Well, satisfying x squared plus y squared is equal to 4, this would be x equal to 2 cosine t, y equal to 2 sine t. So now x squared plus y squared is 4 cosine squared plus 4 sine squared, which is 1, or which is 4, sorry. So that satisfies the first equation. X squared plus y squared is equal to 4. Now z, just write z so that it satisfies the equation with the x and y that we're given. So z is equal to 1 minus 3x minus 2y. So that's 4 sine of t. All right, so x, y, and z defined by these functions of t, 2 cosine t, 2 sine t, and 1 minus 6 cosine t minus 4 sine t will satisfies both equations, and therefore is the surface, the curve of intersection of those two surfaces, the plane and the cylinder. Right? Okay. So that's all for this section. It's a pretty short one. The lecture for section 3.2 is going to have more material in it, of course. Okay.